Hello and welcome. My name is Mitchell and I'm here today to teach you about the Lie algebra. Basically the main fundamentals of what it is and give you a few examples of them and how to go about proving a Lie algebra. Now the first thing to understand is that the Lie algebra is a very well-known mathematical concept. It's been around for well over 100 years, ever since the 1870s, where the man Sophus Lie first came up with the concept. And it has been used widely ever since. It has been used in a lot of physical systems, predominantly in quantum mechanics, used to model fundamental particles. But that's getting a little bit ahead of ourselves. Let's get right into understanding what exactly a Lie algebra is. Well, first of all, we're going to assume that this term here, G, is a Lie algebra, and that means that G is a vector space and we say it's endowed with a bilinear operator, the brackets. So this is known as the Lie bracket. So basically, the way this works is that you put in two elements and it should spit out another one. So this is actually the first property you need to have, that when you put in two elements into whatever this operation is, you're going to get an element in G back out. This is a very important aspect because it just means that it's closed under this operation. So that's actually the first property you need to understand. So we could say here that this is the closure property. But most often you're going to have that, so there's no need to really worry about it, unless you're dealing with certain types of Lie algebras, but we'll get into that a little bit later. So this bracket is not just any generic bracket, it must follow a couple properties. First of all, it must have a property known as anti-symmetry. All this really means is that, let's say that we have a couple of elements x, y. I will put these elements down here. Let's say we have two elements x, y that are in our Lie algebra G. What this means is that if we put these elements x, y into our Lie bracket, then that is going to be, then if we switch those elements around, we're actually going to get the negative of that. So this is anti-symmetry. You're probably used to symmetry a lot in a lot of systems, and that means that they're the same if you swap them around. In this case, you're going to have a negative if you swap them around. Very important property. Now, the next one we need to understand is known as the Jacobi identity. And obviously founded by some guy named Jacobi. And this one can be a little bit tricky to write out, but I think that there's a very nice way to write it out. So this is a sort of identity that makes elements, that makes the Lie algebra sort of refer to itself. So what you can have here is that you're going to have element x be bracketed with the element that is bracketed by y and z. And now what you're going to do is you're going to add that, and you're going to shift each of the elements over one position. So y with z x, and you're going to add that with, shift them again, z with x, y. And after you do that, if this is in fact a Lie bracket, that we call it, it will end up equaling 0. So as long as you have these two properties, you are going to be guaranteed a Lie algebra. So that is the very basic definition. You just have a vector space, and you have this property that takes two elements, produces one of the elements, and it's anti-symmetric, and obeys the Jacobi identity. Now, let's go over a couple examples that you might be familiar with if you're looking at mathematics of this high level. So let's first consider the elements of matrices. So we're going to consider the n by n matrices with real elements. So these are just the n by n matrices with real elements. And we're going to consider the commutator. So what that means is that if we put in two matrices, we get AB minus BA. Now, you can, of course, use this with real numbers, but you might be aware that if you use traditional numbers, this will always be 0, which technically can still functions. It's a sort of trivial case, but we're going to deal with matrices because they're a lot more interesting and they become very relevant in future studies of Lie algebras. So the way the commutator works is that we have a times b and then we subtract it by the swap around of that. So you swap them around, b times a, and you find the difference between them. Now, first of all, we need to make sure that it has anti-symmetry. I'm just going to note it like that. And hopefully that's relatively simple to prove. If we take the Lie bracket a and b, then that's going to be ab minus ba, which is of course minus ba plus ab, because thankfully the addition is commutative under the matrices, as it probably should be in most vector spaces. And so what we have here is that we can bring the negative out and get negative ba minus ab, and that is just going to be the negative of, let me draw that bracket better, ba. Fantastic. So we have satisfied anti-symmetry. So we can go ahead and give this a nice big old tick. Hooray. So now, let's change up the colors a little bit. Now we want the Jacobi identity. Hooray. So for the Jacobi identity, this might seem a little... This can be a little bit more tricky, but let's say we have 3 elements, A, B, and C. You can use X, Y, Z if you prefer, but this is more natural to me. Plus B, A, C. Sorry, my mistake. Plus B, C, A. Plus C, A, B. Okay, so we have all that. So now we have to go through the process of breaking this apart. So of course this is going to be A with bracketed with BC minus CB plus B bracketed with CA minus AC plus C bracketed with AB minus BA. And so we get A multiplied by BC minus CB minus BC minus CB times by A plus B bracketed with CA minus AC minus CA minus AC times by B plus C multiplied by AB minus BA minus AB. Let's hope I have space here. AB minus BA times C. Okay, it's just in there. So let's go down a little bit. And now we can distribute this entire point, this entire place. So what we get here is ABC minus ACB, and of course this is the tedious part, minus BCA plus CBA plus BCA minus BAC minus CAB plus ACB plus CAB minus CBA minus ABC plus BAC. So now if the letters A, B, and C are not, don't sound weird to you at the moment, congratulations. They very much are weird for me at the moment. So what we can do now is have a look at these terms and try to combine like terms. So clearly we have an ABC here and we have an A minus ABC here, so these terms cancel out. Now here we have an ACB and we have a plus ACB. So these two terms cancel out. Minus BCA plus BCA cancelled out. Plus CBA minus CBA, they cancel out. Minus BAC plus BAC. and finally minus CAB plus CAB. And so in the end, after all our wonderful cancel out, we get our result is 0. So once again, we have a nice big tick. So therefore the matrices under the commutator acts as a Lie algebra. So this is a Lie algebra. Hooray. So now let me give you one more example. This is probably one that you're likely very familiar with and you probably didn't realize was a Lie algebra. Especially not if you've only learned about the term today. So let's move on with a nice pink now. So what we're going to look at is the vectors, the three-dimensional vectors with real elements. For a quick refresher, that is all of the matrices A, B, C. So we're going to be using column vectors as a notation, where A, B, and C are real numbers. And what we're going to be using for our notation, so U and V, so we're going to have vectors U, V, and W be generic elements of R3. Our Lie bracket is going to be U, and V is the cross product, or also known as the vector product. So you're probably very used to this notation. You've likely learnt it in first year maths courses or in high school mathematics, and so you're probably very familiar with it. So this should be easy to go through. So first of all, let's try and check if there is anti-symmetry. So first of all, anti-symmetry. Thankfully, this one's not too difficult because, as we're all aware of, the cross product is already an anti-symmetric element. So if you cross the terms over, V cross U, you get the negative. And you can understand that by the right-hand rule. So if this was U and this was V, let me use different colors for that. If this is U and this is V, then of course our cross product is going to be following by the right hand rule. So thumb, index, middle finger comes out here. This is U cross V. Now, however, if we're doing V cross U, well, thumb and index will result, I can draw that better, coming down here. Now, this isn't a super detailed, granular definition, but you, as an exercise for the reader, you can go in and show this explicitly with whatever way you understand to solve for cross products. But the main idea here is that we do have negative VU. Now, you don't have to use the notation of the Lie bracket all the time. You can just leave it as the cross product and say the cross product operation is your Lie bracket, quote unquote, or your bilinear operation that turns this into a Lie algebra. But for simplicity, we're going to keep the Lie bracket definition, the Lie bracket notation for now. So now, of course, is the Jacobi identity. And so for our Jacobi identity, we have that U VW plus VWU plus WUV. Now we need to prove that this ends up equaling 0. So this one's actually a very fun one to do. So we can, and this is where we have to be quite careful here, because if you do U cross of V cross W plus V cross W cross U plus W cross U cross V. So now it's very important to maintain these brackets, because something that you might not have fully appreciated when learning about cross products is that the cross product is non-associative. I'll quickly take a moment to explain that. So you might be aware of the IJK triple, which is that I cross J is K, J cross K is I, and if you go backwards, it's negative. So we're going to work with a very quick example. Let's consider I cross J cross J. Now, as we all know, any element crossed with itself is just going to be 0. So we have I cross 0, and anything cross 0 vector is going to be the 0 vector. So now let's change the order of the brackets, the order of the operation. I cross J cross J. Well, I cross J is going to be K, so we have K cross J, and so K cross J is negative I, which is not 0. So that's something to be very clear here. We do not have an associative operation. This Jacobi identity kind of acts as a substitute for associativity. Sometimes you will have associativity in your definition, like how before with the matrices, matrix multiplication is associative, but here we don't have it, so we have to be careful how we proceed. So the way we're going to solve this is by remembering one quick notation. So if I come down here, we might remember a definition where if we have 3 elements, A cross B cross C, this will be equal to A dot C times B minus A dot B times C. Now, if you have never seen this operation, known as the Lagrange equation, or Lagrange identity, you'd be worth going in and proving this yourself. It's a very fun little exercise. You can also go about proving this in a very granular way using the known notation of if you have U cross V, then you just make a matrix IJK, U1, U2, U3, V1, V2, V3. And yeah, that would be a valid way to do it, but it is long and tedious. So we're going to eschew that. If you were to do it this way, you wouldn't be wrong. It would just be very long, but I wish you luck if you'd like to try it that way. So using this definition, using this known identity, we get here U dot product with V times, U dot product with W times by V minus U dot product with V multiplied by W plus V dot product with U times by W minus V dot product with W times by U, running out of space a little bit, plus W dot product with V times by U minus W dot product with U multiplied by V. Now, thankfully for us, we know that the dot product is a commutative operation. So A dot B is equal to B dot A. So we can start doing some cancellation here. So U dot WV is the same as W dot UV. So these two terms are going to end up cancelling out. Let me use a different color for that. No, we'll stick with yellow. So we'll cross these two out. U dot VW is the same as V dot UW, and since that's negative and plus, those terms cancel out. And here, V dot W, that should be a W, and W dot V, these terms cancel out. And so, in the end, we're very thankful to have this equal to 0. So, hooray, we have both anti-symmetry and the Jacobi identity. So the 3-dimensional vectors with real elements under the vector product is a Lie algebra. So now one more main concept before I give you some practice questions. I'm going to give you one more example of a Lie algebra. and I'll leave it to you to prove that it is in fact a Lie algebra. So what we have here are known as the general linear Lie algebras, GLN. Now, sometimes they are instead written as GLNR in order to indicate that this vector space is over a field R. Most often, when we don't include it, we assume R, or C, depending on which field you're working in. So you might want to include it, but here we're just going to treat it over the field R. So what is this abstract concept? So the way we define this is that it has a basis element. It has a basis of these elements E, J, K. I'm using this upstairs downstairs notation, where J and K go from 1 to n. So doing quick sums, it has an n squared basis. It has n squared basis. And we just take the span of that. So all linear combinations of these elements E, J, K. These elements don't have any formal understanding in traditional notation. These are just elements, and you should treat them as such. And this GLN has a bilinear operator that is understood to be, that is defined as EJK with EPQ. That is defined as the Kronecker delta of PK EJQ minus the Kronecker delta of JQ EPK. Now, a quick refresher on the Kronecker delta. The way our Kronecker delta is defined is that if Kronecker delta of JK is a cases function, where it produces a 1 if j is equal to k, and it's 0 if j is not equal to k. So you can see that if p and k are not the same element, then this just all turns to 0. So therefore you need some of these terms to be equal to each other. Now I would like you to now, proving it's anti-symmetric should be relatively easy. Doing the Jacobi identity will be a bit more challenging, but should ultimately prove the same thing. And I will leave it to you to prove it. Now, why do I want to give you this example? Well, it's because this is one of the most fundamental, foundational Lie algebras that a lot of other Lie algebras spurn off from. If you are interested, you can look at stuff like the special linear Lie algebras or the symplectic Lie algebras, and many others. If you go to a page, you can start seeing these, and these are all basically subsets of the underlying GLN, and they're very much worth studying because they're used a lot in physical systems. But we're going to keep it simple for now, and the GLN. There's also another very important caveat to understand when looking at GLN, and that is that GLN is often misunderstood as the n by n matrices over R. So I'll just state this pretty plainly. These two are not the same thing. These are not the same thing. But they are related. It is true that there is a good relationship between them. Now, the reason they're not the same is because if you were to imagine two elements in M and N, you can multiply them together, and that will be, if you have two elements of M and R, you can multiply them together and get another n by n matrix. However, with GLN, there is no understanding of a multiplication between elements. So EJK and EPQ are elements of GLN, but they are not elements of GLN itself. In fact, there is no a priori, so before anything, there's nothing in here that defines a multiplication between these, so this doesn't even make a lot of sense. You have to go to other levels of mathematics. However, what it is often said is that the n by n matrices are a good representation of GLN. Now, this is going into a whole other field known as representation theory, but what that basically means is that if you were to take elements of GLN, you can represent them. So, let's say let's say we're working in GL3. Let me use different colors for this. So let's say that we're working in GL3, right? Well, we can treat elements such as E13 as if they were the matrix element 0, 0, 1, 0, 0, 0, 0, 0, 0. So this is known as a representation theory, and oftentimes in a lot of physical systems, these are used to construct certain models and are often used to better understand Lie algebras because we understand matrices a lot better. So you'll often find GLN defined as the n by n matrices, and they act like them in a lot of ways, but they are not exactly the same. It's an important distinction to make, but one you probably won't come across a lot. If you're interested in this area, feel free to look up representation theory and start looking into that. But first of all, I would like to leave you all with a few exercises to make sure that you understand Lie algebras and how to define them. So I'm going to give you 3 cases here. So first of all, I'm going to call this one G1, and this is going to be defined as all of the upper triangular matrices, all the upper triangular 2 by 2 matrices. So in definition, A, B, C, 0, such that A, B, C is a real number, and it has the Lie bracket AB minus BA. Now, proving that this is this satisfies the conditions won't be too hard. However, it was that very first property, and that is closed. And this is one that we haven't covered a lot, but I'm going to leave it to you to try out these ones. Next is the strictly upper triangular matrices of 3 by 3 matrices, where A, B, and C are real, and the same Lie algebra as before. And now finally, one that's a bit more interesting, G3. We wanted all of the GL3, and just to be very clear, GL3R, so over the field R, matrices such that the transpose is equal to negative x. Just to be very clear, and of course this has the same Lie algebra as known before, and so we're very clear, EJK transpose in this case is going to be EKJ. So using that definition, I would like you to prove that this is in fact a Lie algebra. So traditionally the closure aspect. All you have to do for each of these cases is show that if you take 2 generic elements of these and you split them into your respective Lie brackets, you get this. Now, this one will be a bit more interesting because you should try to have a go at looking at what the new basis is for this and start working from that. But I will leave that as an exercise for you. Alright, best of luck, and hopefully tune in for more. Thank you very much, and I hope you learned something. Take care. Bye.